second. Is it visible?
हाँ सर, फुल स्क्रीन कर लीजिए. Perfect. Start कीजिए. Wait a minute. Let me first introduce you to the audience. So, hello everybody. My name is Anil Sharma. I'm the chapter chair of IEEE MTTA Student Branch Chapter, IEEE TDM Jabalpur. The topic of today's webinar is recent advancements in planar microwave filter technology. The introduction of our speaker is Dr. Anil Rajput, the IEEE member, has pursued his PhD on investigation on bandstop filter for wideband and reconfigurable characteristics from PDPM IITM Jabalpur, India. He has served as an adjunct assistant professor at IIT Pune, India. Currently, he is working as a Post Doctoral Fellow at IIT ISM Dhanbad, India. His current research interests include filters, reconfigurable circuits, metamaterials, and antennas. He has authored and co-authored over 25 research articles in international peer-reviewed journals and conferences. He received the Best Thesis Award for his PhD thesis at IEEE CICT 2023 conference in December 2023. So with this, I request Dr. Anil Rajput, sir, to start his presentation. Thank you, sir.
Thank you, Amit, for this nice introduction. And thank you, IEEE MTTA Student Chapter at IITM Jabalpur for giving this wonderful opportunity. So I have chosen the topic of presentation, recent advancements in planar microwave filter technologies. So these are the outline which I will cover in the presentation. First one, introduction. In that we will understand the basics of the filters, and then the possible solution of the recent communication system issues, and then motivation, and then recent research on the filters, and then we have to move electronically reconfigurable filters, and the future scope, and then the references. So due to the exponential growth in the wireless communication system, there are so many frequencies available in the nature. Like these are the different communication system. They have different communication frequency, and these frequency may interfere their nearest communication frequency system. So we have to remove, or we have to minimize this interference. So by doing the filtering, so we can filter our desired signal. So these are the classifications of the filters. So the filters are the four types, like low pass filter and high pass filter and band pass filter and the band stop filters. So these are the simple lumped equivalent model of the all four types of the filters and their responses. Like this low pass filter passes the lower frequencies and stop the higher frequencies, and the high pass filter stops the lower frequencies and passes the higher frequencies, and this the band pass filter passes the a certain frequency band and stop the either side of this frequency band, and the band stop filter stop the certain frequency band and it passes the either side of this frequency bands. So this is the communication system where we can understand the how we utilize this band pass filter and band stop filters in any communication system. So here we have two a signal, which is blue one is our desired signal and red one is our undesired signal, and this undesired signal has the very high amplitude in comparison to our desired signal. So we have to reduce or we have to minimize this undesired signal. So these both signal is received by the antenna and filtered by the band pass filter, but it will not attenuate this undesired signal because it has the higher amplitude, very higher amplitude in comparison to the our desired signal. So we have to utilize the band stop filter for this band so that it can reduce or it can minimize the this undesired signal, and then we will receive the our desired signal. Right. So there are two filter we can use. So there are three possibilities to design the band pass filter, band stop filter. First one is the wideband and ultra wideband pass filter and band stop filter, and the multiband band pass, band stop filters, and then the electronically reconfigurable band pass and band stop filters. So these are the basic terminology to characterize the filters. First one is the bandwidth. We can define the bandwidth of the filter and the center frequency and the quality factor of the filter, and then the skirt factor. Skirt factor nothing but is slope of the transition of band. Means this is the pass band and this one is the stop band. Then this is the slope. So we have to define the skirt factor by this slope, and the return loss and insertion loss of the filter. So these are the some components where we can generate or we can achieve the inductive or capacitive effects by doing the several arrangements. We can generate or we can make the filters. So like how we can generate the inductive effect or capacitive effects. These are the microscopic components. So like this one is the higher impedance line. So it generates the inductors. So this inductor lines or high impedance line we can fold as a meander line, and we can fold as a square spiral line, and this is the interdigital capacitor. Here we can generate the capacitance. And here the discontinuity. So like this one the step impedance. So we can generate the capacitance at this edges. Here open-ended stubs, so that we can generate the capacitance at the end of this open stub because of the fringing fields. And this is one is the edge coupled lines, so that it generate the capacitance between two edge coupled lines. And this one is the band lines, so that means it has the variation of impedance at this band, so it can generate the capacitance at this point here, like this one. Another the low or high impedance line sections. So this is the high impedance line, that means it generates the inductance effect or inductor, and it this one is the low impedance line in compared to the current characteristic impedance 50 ohm line. Then it generates the capacitive effect, and these are the circuit and the short circuit ended lambda by 4 line stub, and this one is the open ended lambda by 4 line stub, and it generate the transmission poles, and this one generate the transmission zeros in the filters. And these are the some resonators where we can use the resonator in the designing of the filters. Okay, like this is step impedance resonator. These are the open-ended stubs, and these are the short-ended stubs, and these are the circular ring resonator. This is the circular patch resonator. This one is the triangular patch resonators. Now, motivation behind to do the work in the on the filters. So we have to design the filters to reduce the electromagnetic interference and to minimize the crosstalk between two communication systems. And then we have to design the filter which has the higher square factor and which has the wider bandwidth, and which has the pass band level, high pass band level, so that maximum power will be passed, and in the stop band range it has the high rejection depth. And we have to design the wideband band stop filter, multiband or multiband filter, and the electronically reconfigurable filters. Okay, and all the filters should be highly compact and easily installable and widely compatible to all the components or devices. So I will show you some work on the filter, band stop filter, and some work on the band pass filter. So I will start by the band stop filters. So here, first one is work focus for the ultra band response, and these are the parameters which I have taken to design this filter. And here I have taken three open-ended stubs. First one is this one, and this one, and this one. These three are the open-ended stubs which generate the transmission zeros in the filter response. And I have introduced this new type of resonator, which is inspired by the Yajuda resonator. Here, if the power will go to this T section, then and it will direct the power to this section and then this section. That means maximum power will be absorbed or stored by this resonator. Okay, and in the from figure B, we can see that it shows the time distribution across the design at the frequency of 6 GHz, and it validates that there is no current pass from one end to another end at the frequency of 6 GHz. And this is the lumped model expression of the filter. So here we have three open-ended stubs. That means it has the inductive or series inductive or capacitive combination. So these are the three open-ended stubs combinations, and then it has the impedance step impedance. That means there will be capacitance will be there. That is, this is on the capacitance, and here also capacitance. This one, and this is the high impedance line. That means it will act as a inductance, and then this one also high impedance line. We can this line also act as a inductor, and then this is the open ended. That means inductor capacitance effective combinations, and then the coupling between two adjacent two lines. That means capacitance, and then the resonator, then capacitance, the resonator, then all. Or similar, because this filter is symmetrical from the center, so we can also relate this component also. And we have simulated this lumped model in the software, CST software or ADA software, and compare with the distribution line model, and it has the almost similar result to the distribution line model, and which validate the simulated result of the filter. So now to validate this simulated result, we can also accept the transmission model because it has the symmetry. It is symmetrical from the center, so we can analyze even mode and odd mode analysis. So like this one is the even mode arrangement. This one is the odd mode arrangement. If we calculate the even mode impedance and odd mode impedance, and if we put this values in the S11 parameter or S21 parameter or S11 parameter, we can get the parameters, these as parameters. So like here, if we calculate the input impedance at this age, and then this impedance and this impedance, this four line are in the parallel, okay, to calculate the even mode impedance. Clear? So here, this there 3 shows the characteristic impedance of that line, and theta 3 shows the electrical length of this stubs or line. Okay, and then we have calculated this even mode impedance or odd mode impedance from the MATLAB, and here we can see that the even mode odd mode impedance is very almost similar and very low. And if we put this impedance in this formula, then we will get the transfer zeros positions. According to this, we can validate the band stop filter response. And it is fabricated and measured, and measured and simulated result are in very good agreement. And this ultraviolet band stop filter offers the 112% fractional bandwidth, and it has the cut factor of 70 dB per gigahertz, and then it has the 5 transmission zeros. And second one work is the multi-wideband band stop filter. So to design this multi-wideband band stop filter, first of all we have to design the ultra-wideband band stop filter by this arrangement. Then we have to generate the notches in between this ultra-wideband response. So how we can generate? We can generate by introducing annular shape cross coupled lines, so that it can generate the notches in the range of this stop band range. Okay, like here. So it generates the notches in this stop band range. So it will act as a now multi-band band stop filter. So it generates notches at the 2n plus 1 lambda g by 4, where n is the single resonance and the dual resonance, triple resonance, and it create the notches at the frequency of 3.3 and 5.6 and 7.8 gigahertz. Here from figure B, we can see that it has a single resonance, this one, and it has a dual resonance, and this one dual resonance, and a triple resonance, this one resonance, and this one, and this one. Okay, so it generates the notches in the band stop range, and it will act as a multi-band band stop filters. And it is also fabricated, and it offers the 3 band stop range filter, 3 band stop response, which has the center frequency of 2.24 and 4.8 and 6.52 gigahertz, and which has the fractional bandwidth of 79, 26, and 13% fractional bandwidth. Now, I have designed the electronically reconfigurable single band to dual band band stop filter. So electronically reconfigurable means we have to control the response of the filter by utilizing the electronically by without changing the physical dimension of the filter. So how we can change? We can change the this or we can control this response by utilizing the biasing different biasing voltages. Okay. Now here we are utilizing the pin diode. That means it acts as a on or off condition. So if we give the forward biasing of the for this pin diode, then it acts as a on state. And if we give the reverse biasing of this pin diode, then it acts as a off switch. So now to get this single band to dual band stop filter, first we design the ultra band stop filter, this one, from this, and then we have to design uh, a biasing network to get the biasing this pin diode. So why we are doing this designing this biasing network? Because this biasing voltage are DC supply, and this RF source is the AC supply. So we have to isolate both sources. So here we utilize the RF choke or inductor. That means the RF power will not go to this DC supply. Okay, and we have utilized the DC means DC blocking capacitor. That means DC power supply will not go to this RF sources. Okay, so that by this arrangement we can protect both RF source and DC sources from each other. Okay, now this is the current distribution of the across the filter. If diode is on state, that means power will go to this line to this to another end. Okay, and then when diode in off state, then there is no power goes to this end. Okay, at the same frequency. Okay, 3 gigahertz, or this one is a 3 gigahertz. Now and that means if we pass this current through this stuff, that means it passes the certain frequency which has the length of this one, because we are uh, working on the lambda g term lengths. Okay, and when they diode in on off state, there is no current pass. That means it act as a, or it generate the transverse zeros. Okay, so here, this is the equivalent model of this pin diode for off condition or on condition. When diode is on state, it passes a certain frequency band, this one, and which covers the 3G and 4G and 5G mobile communication applications. And when diode in off state, it stops the entire band. Then it gives the wide band response. Like so here from this figure, we can see that it when diode in on state, it offers the dual band. The first one is this one, and second one is this one. And when diode in off state, it offers a single ultra wideband response. This is a table where we have the different resistance and inductance and capacitance value for the both stages, off state or the on state. Now we move to the band pass filter. So here this work is published in the IEEE MWCL letter, which is published by the MFN and all. So here they have mentioned the band pass to band stop. That means they will do the switching. For switching, we utilize the pin diode, and then they have mentioned the tuning of the range. The tuning we can achieve from the vector diodes by diodes, so, because we know that the vector diode, if we give the reverse biasing of the to the vector diode, it varies the capacitance with respect to the different voltages. So according to this, the capacitance will vary. This and this one, this one. So they are the vector diodes. This one and this one, this one. So that it varies the capacitance. According to this, resonance frequency also will vary. Okay. So when diode is off state, it offers or it acts as a band pass mode. Okay. So that means it has a two paths to travel the power one port to the another port. And when diode in on state, it offers or it acts as a band stop mode. Okay. So by doing this, we can we can get this tuning of this bands by utilizing different voltage on the vector diodes. Similarly, for in the band stop mode, we can get different bands on the different voltages. Okay. Now, this is the current research. People are working on the reconfigurable filters or reconfigurable antennas. Okay, and with the filtering characteristics. So here, the author has done this work for the ultra wideband with circularly polarized antenna. Okay, and this work is published in the transaction means TAP in 2022, and they have this portion act as an antenna, and this portion act as a reconfigurable filters. And when this filter has a ultra wideband response, then it passes this entire band, and it has the gain, stable, almost stable gain in the entire band, and they have achieved the circular polarization and the ultra wideband responses. Now, how means they approach to design this reconfigurable filter? So first they have designed the simple feed based antenna. Okay, and then they have created, or they have achieved the circular polarization by utilizing the perturbed slots. Okay, and then they want to create the filtering in the entire band of this antenna. So they have integrated this filter at this plate, or at this place where they replaced this field line to this filters. And then here also they have mentioned this the yellow color shows the vector diode, and the green color shows the pin diodes. They have arranged three type of arrangement where they achieve the band stop response, and then the band pass response, and then the ultra wideband band pass response. By doing this, they have achieved the different type of the response. Now this one is the different bands on the different capacitance value of the vector diodes, because they are using the same vector diode in the entire design. So they have taken the at a time of the different capacitance. Means this one is at this time, and this one capacitance utilized for this band, and this one capacitance utilized for this band. Okay. So according to for the here they are also utilized for band stop response, also band stop filtering also. So this one is the radiation pattern, and they achieve the circular polarization. Uh, so this one is the radiation pattern, and they radiate the power on the top side and the bottom side also. So here this one is the LSCP and RSCP radiation pattern, and this one is the band tuning across the uh, frequency range, at this frequency range, and this one is the band tuning in a stop band condition for this frequency range. Okay, uh, and the future scope will be we can utilize we can design a reconfigurable band pass or band stop filters, and we can design reconfigurable filter for both switchable and tunable characteristics. And then we can utilize the we can design the diplexer, and we can design the multi-band band pass filter, or reconfigurable band pass filter, which covers the our recent communication applications. Okay, these are the references, uh, and thank you. If anyone have query, then please ask. Amit?
Yes, yes, sir. Thank you, sir. On behalf of IEEE MPTS Student Branch Chapter, PDPM IITDM Jabalpur, I am Amit Sharma. Thanks, Dr. Anil Rajput, sir, for delivering such an elaborated yet brief talk on recent advancements in planar microwave filter technology. Sir has shared his ID also at the end of the presentation. So I request if any participant have any doubt or questions, so they can go there and ask sir. Thank you, sir, for such an elaborated talk. Can close the session now. Thank you, sir. Thanks to everybody for joining us.
Further, anyone have any query, then please contact on this mail ID, on my mail ID, and mail. Okay.
Thank you, sir. Thank you, sir.
Thank you so much. Thank you so much for this nice opportunity. Thank you.
Okay, sir.
Mm.